Here are the words to know for our unit on motion. The words are reference point, speed, frame of reference, relative motion, velocity, acceleration, distance time graph, speed time graph, meter. Here are the key questions. How do we know something is moving? What is relative motion? How is speed calculated? What are the types of speed? What are velocity and acceleration? How do you read a distance time graph? How do you read a speed time graph? How do we know something is moving? This might seem like a very easy question to answer. It's something we know intuitively. We just know it because we see it happen. But in science, that's not good enough. We have to be able to define exactly what makes something move. We know something is moving because its position changes in relation to something else. It was in one place, and now it's someplace else. That's how we know that motion has occurred. And we need to think specifically of relative motion. And what is relative motion? You need a frame of reference, or a reference point, to know how something is moving in relation to something else. So before you can say whether something is moving and how fast it's moving or how it's moving, you need to have some point of view determined from where you're going to say it's moving. So everything is moving relative to something else. So all the time, everything is always moving, but it's only moving from certain reference points, certain points of view. Let's take a look at a video. In this video, watch and see if you can see which trains are moving and which aren't. The video is being recorded on a train. Is the train across from you moving? Is the train you're on moving? What do you think the people on the other train are seeing? Are they seeing you move, or do they think they're moving? You can probably tell from the background now that the train that you're on is no longer moving. Let's take a look at another example of relative motion. What's moving in this picture? How are things moving relative to each other? The car is moving relative to the road. What's moving now? Are you still moving, or is it just the snowflakes that are moving? Without a clear frame of reference or point of view, it can be difficult to say whether something is moving or not. Let's look at one last example of relative motion. Here we have several things that we can look at in this simulation. Here's you here. There's a car, there's a truck, and we can, think of these as just other points of reference, these dots here. And we can look at motion relative to different things. Now here's your observers here, and we can play this, and you notice they're standing still, but everything else seems to be moving. Now, if you were in the truck, you're not moving if you're in the truck relative to the truck. You're still in the truck. However, you are moving relative to the observers here, relative to everyone else walking and that other car. You're here, everything else seems to be moving if you're walking by. If you're in the car, everything else is moving differently from your point of view. And this makes sense. If you're in the truck, you're going to see things moving differently, coming towards you or away from you, different than the car. That's going to see things differently coming towards or away from whoever's driving the car. So it's very important that we determine what the frame of reference is, or what the point of view is that you're determining motion from. That's relative motion. Once we've determined our point of view, our frame of reference, then we can learn things about the motion. Things like speed. Speed is a rate. It's calculated by distance divided by time. An example, you might take 180 seconds or 3 minutes to walk from science to technology class. That's 360 meters away. Your speed is 2 meters per second, because 360 meters divided by 180 seconds gives us 2 meters per second. Notice how meter is abbreviated with an M, and this slash here means per, and the S is short for seconds. So that's read meters per second. We can also call this our average speed. Of course, you don't always go at the same speed from class to class. So we have to have a term called instantaneous speed. More than likely, you stop at your locker, talk to friends, or you walk more quickly to catch up to someone or to get to class on time. At any one of those instances, your speed could be 0 meters per second if you're at your locker, or over 2 meters per second if you're walking fast because you're late for class. Instantaneous speed is therefore the speed of an object at one instant of time. Sometimes you'll hear the word velocity used, and often it's used interchangeably with speed. And this is usually incorrectly done. Velocity has a specific definition in science, and that is speed in a given direction. For instance, 15 kilometers per hour north would be your speed with a direction north. Acceleration is calculated by finding the change in speed and dividing it by the time it took for that change to happen. And we abbreviate usually at the final speed minus the initial speed, and we divide that by time. Our units for acceleration are meters per second, and we can change that to meters per second squared. And we can also simplify this. Instead of thinking of it mathematically, just think of any time something speeds up, slows down, or changes direction, that is acceleration. How do you read a distance time graph? A distance time graph is useful for comparing the speed of objects. In a distance time graph, time is always on the bottom x-axis. Distance is on the side y-axis. Here's an example. Notice distance is on the side, time is on the bottom, and we have 3 different vehicles here. All right, you can think of these as bikes, you can even think of them as people running. And a few things to note: the steeper it is, the faster it's going. If it's curved, it's accelerating like this. If it's flat, it's stationary. You notice the distance isn't changing as time goes on, so we can see that as being stationary. And also the lower it is towards the time here, I think lower, slower. So the lower it is down here, the slower whatever that's moving is going. How do you read a speed time graph? A speed time graph is useful for comparing the acceleration of different objects. So whereas this compared the speed, here we're going to compare the acceleration. So we're going to plot time again on the bottom, or x-axis, and speed is going to be on the side. And we can see here, speed on the side, time on the bottom. This is a uniform acceleration. If it's flat, it is a steady speed. It's not changing, right? Staying the same speed. Maybe someone put on the cruise control on their car and they're going the same speed. And if it's going down, we read that as a negative acceleration or deceleration. Someone's putting on the brakes and they're slowing down. Right? Their speed is getting less and less. Here's some other examples that we can look at. We have velocity and time here. You notice the velocity keeps increasing. That's acceleration. This is something where we're measuring not from zero, but it's already starting to be measured at some velocity. This is a deceleration. And think about what's happening here and write that down in your notes. Label each one of these sections, and you can use the previous graph as well to help you. And that concludes our notes on motion.